In this video, I'm going to be showing you how to add a new device simulation to the QEMU source code. So I'm going to be working on STM32 because STM32 support is not very well supported in QEMU at the moment. There are two basic repositories that implement some support, but I think that the current support that is available is not very good, and primarily it also doesn't allow you to really trace in detail what the firmware is doing. Because what I find is very useful is when you run a firmware on QEMU, you can actually audit everything that the firmware is doing to the GPIO pins. So the most recent thing that I've added, for example, is the driver for the power registers. So I can see here that when the firmware is starting, it's enabling overdrive. It is then also setting, let's see, I can also see, for example, errors when the firmware is trying to set PLL-M while PLL is disabled, which it shouldn't do. So a lot of things like this are very useful for debugging and for kind of understanding what the firmware is doing. So what I'm going to be doing now is adding GPIO support, and as you can see here, I have lots of reads and writes to registers that correspond to GPIOs. We can take this number and input it into the datasheet for STM32, and we will see that this address that it is actually reading and writing belongs to GPIOs. It is the address 42, and then we can do like this, and we'll find 00, and we'll find that this address actually belongs to, let's see, this one is actually DMA, so that's not GPIO, but we can see 424. Let's see where that is. Actually, no, sorry, I was wrong. 424 is probably something else because DMA only stretches until 3FF. So we can go farther, and we'll see here if we can get anything there. Let's see, 402. Let's see. This is actually the wrong data sheet because this is for this is a reference manual for F3, I think. Let's switch to another reference manual. This is a reference manual for 427, which is the architecture we're trying to simulate right now. So if we go here, we can see that this register, which is, let's see, can we get something? This register, which is at 402.0424, actually belongs to GPIO B. And what we want to do is create a driver that will map into this memory area and take care of all the register writes and reads for the GPIO ports. So what we're going to do is we'll go to the source code of QEMU, and we will add a driver for the GPIO. Now there is already a driver for GPIO, which comes from a different repo, but I think this GPIO driver is really convoluted. It doesn't really use the latest QDev framework, and it doesn't actually compile out of the box. So a lot of changes are needed to make sure that this driver actually works. So we'll create a new driver. We'll move that one to GPIO old, and we will just create a completely new driver from scratch. And we can use the power register as, or let's see, let's go to FMC, because this is a driver that I've created, which is just a placeholder for the FMC, and we can just copy the source code, and we'll go to the GPIO, and we'll create a new driver for the GPIO. STM32 FXXX GPIO, we can call it, and then we paste this code in here, and we can replace everything that is FMC with GPIO, so we get this skeleton for a driver, which is going to take care of all the memory writes to the GPIO registers. And we'll instantiate this driver several times for each GPIO port so that we can cover the full range of GPIOs which are present on this STM32 chip. So let me just replace this remaining reference to FMC with GPIO. And what this does, the way that you instantiate new drivers in QEMU is that you create an object like this with type init, and to this you pass a function which is going to be called to initialize this type, and from this function you just register a type register static, and to this function you supply a pointer to this descriptor structure where you have the name of your type, which you can then later use to instantiate your object. You have a parent, which in this case we just set to bus device, which I think actually is the, let's see, yes, so this type here, which basically corresponds to string SUS bus device, is just here to describe the relationship of subclassing the SUS bus device, which is the first member of this structure for STM32 GPIO. It is a SUS bus device, so we supply parent here and we set it to the string description of that class, and this allows us to test pointers whether they point to the correct type, and we can also do dynamic casts between types of, for example, just a device. We can cast it to SUS bus device and we can cast it to GPIO and do it in a very robust way where if you supply the wrong pointer you're going to get an error from QEMU framework. Then we have the instance size, which is the size of this object. We have init function and we have class init function. So let's talk about, in the class init is just a very simple function. It just defines a device class or actually it casts this object class to a device class, this parameter, and then it sets reset function, it sets the properties, and it sets the realize function. We might want to add some properties here later, and actually we're going to add a property for the STM32 state variable, which is stored in the STM32 sock class, which will represent the state of all of the peripheral registers for the STM32. I'll explain the reason for that a bit later. But if we go farther to the reset function, we have this reset, which is empty currently, and we have the realize. So the way that QEMU is going to instantiate this object is it's going to first call the init when you instantiate the object, and then when you have initialized all of your objects, you will call realize, and when the object is realized, it's going to call this realize callback. And there is a very good reason for. Okay, somebody is actually making holes in the building, so you might hear this drill sound. Anyway, there we go. It's so annoying when somebody starts drilling in the middle of the day. Anyway, so let's now configure this range for the I/O. So in the init we have this, we initialize the RQ structure, and we also initialize the memory region for this device. And we can see that for GPIOs we have a memory region which is of size, let's see, so we have 3FF. So the size of the GPIO region is 3FF. And we initialize the memory region here. So we call SUSBus init mmio for the device object, and we supply this member variable to initialize it for us an mmio. This function just adds the memory region to the device memory region stable, so that QEMU knows about it. So what we can do now, when we have set up this very simple skeleton, is we can actually map this skeleton to all of the GPIO memory ranges, so that when we run this firmware, we can actually print that we are trying to write to a GPIO register and read from a GPIO register in all of these lines that currently say ROG memory read or write. This message is, by the way, printed from a memory region which I've set up, which covers all of RAM, which then acts as a default memory region. I set the priority of that memory region to -1, which means that QEMU will try to access existing memory regions, and if it cannot find an existing memory region, it's going to default to this rogue memory region. And this is defined in the STM32 SOC class. Let's see, FXXX C. It's defined right here. So I am actually setting up this region that, let's see, here. So here is the memory region init.io, and I set it up to the size of the full 4 GB range. So any address within that range will end up in the callback functions, which I have supplied here. Rogue mem ops. Let me just update the tags so we can see the, so we can easily jump. So there we go. The memory region defines two operations, which is read and write, and those operations will be called whenever this emulated firmware is calling read or write to any address that is not currently mapped to anything else. And this is a very good way to kind of identify any memory regions which the firmware is trying to read or write, and then to implement whatever is supposed to be on those regions. So let's add the GPIO to our STM32 SOC class, and for that we're going to add a new variable to the structure for this SOC, which we'll call sysbus device GPIO, and then we can do let's see, num GPIOs. So we'll have an array of GPIOs, and by the way, I want to just replace F4XX with FXXX. So we'll do that while we're at it. Right, so we'll keep this as F4XX for now. Let's see. So I'll keep this for now at F4XX. The idea later is to actually add classes for every chip, and then we'll have small variations between chips in terms of where things are being mapped, and we will then improve on this naming convention here. So let's see, we want to add our GPIOs to the memory map of the main device. We can do this in this init function. So we'll go ahead and we'll add the GPIOs to as child objects of this chip. So I've created a small helper function, sysbus create child object. This is actually not in the official repository, but what it does is it basically adds a child object, and it sets the parent bus of this child object to default bus. So then we say that we want to add fxxx GPIO, and this string corresponds to the type name of the object that we want to create. And it is the same type name as we specify later in the definition of our GPIO class. And then we want to add some code to this realize method, which will be called after all the objects are instantiated. And here we will add the actual mappings for the GPIO devices. And we'll go through all of these GPIOs, and we'll map them to the corresponding addresses. Now, all of these mappings are going to be different depending on the chip family that we are running on. So eventually, we would want to modify this whole method so that the mappings are individually configured for every family of the STM32 chips. But currently, we are simulating STM32 F429, so we are using the values that are supplied in the datasheet or the reference manual for the F429 chips. So let's start. Let's go ahead and just map all of these GPIOs to our GPIO object, where we just do like this, and we set GPIO 0. Let's see. And then we need to also define this. How many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 GPIO ranges. And then we can just go through each one of them and just instantiate them. I find it much cleaner to instantiate them like this instead of inside a for loop, because this makes it very clear where each GPIO device is mapped for this particular chip. So we can easily see that we're mapping to the right address. And then we see here we have GPIO A, GPIO B is at 400. Let's see, they're all at 402. 4002. That one is, oh, sorry, there. 400, and then we have 800, and we have C, and we have 20, and then we have 1 there, and then we have, let's see, we can do like this. I think this would be at 400, 800, C2, and then we have 2, 400, 800, and C. And let's see if we are, let's see, 5, 6, 7, 8, 9, 10, let's see, 11. And I think this is 1 too many, so we do like this. 2 to 8, this was, yes, that's GPIO K. A, B, C, D, E, F, G, H, I, J, K. Great, so now we have mapped all of these devices. So we can go back to our GPIO class, and we can see if, let's see, we also need to add the GPIO file to compilation. So we'll do like this, plus STM32 XXX GPIO, and then we'll do like this. We'll try build it, and it's probably gonna fail. And so we can just, let's see here. Let's see. So this is, by the way, how you convert device state to the class that's derived from our device state. You call object check, and here you specify which device, which class you want to convert into. So this is kind of similar to dynamic cast, or yeah, that would be dynamic cast, I think, in C++, where you also do type checking. And this is why we also specify the function here, or the parent member in this structure, so we can do that check. So let's see here. Let's try to compile this and see what else we need to test, what else we need to replace. So this would be def, of course.